In this video, we're going to do an introduction to exponential functions. Now, we're going to start by looking at a pattern. Here I've drawn a pattern of boxes. And you'll notice I've listed off three different figures. I have figure 0, figure 1, figure 2, and then we're going to ask ourselves some questions about like how many boxes would be in figure 10, or what would figure 10 look like, or how many boxes would be in any given figure. Okay, and ultimately we want to find a function, an equation that could give us these numbers. So when we look at this pattern, notice for instance that in the first figure, figure 0, or our starting figure, we start with 2 boxes. We have a total of 2. Then in this figure 1, we now have 2, 4, 6 boxes. And then in figure 2, we have 2, 4, 6, 8, 10, 12, 14, 16, 18 boxes. Now, when we look at the numbers 2, 6, and 18, we hopefully will notice when we look at this pattern that we are tripling our previous amount. So for instance, if I take 2 times 3, that gives me 6. And when I take 6 times 3, that gives me 18 in the next figure. So if I wanted to find the next figure over, call this figure 3, I would simply just take 18 times 3 to get the next figure of 54 boxes. Now, what we want is an equation that can do this for us. Because let's say I wanted to find figure 10, or maybe I wanted to find figure 100. If I wanted to know how many boxes were in figure 100, using the method I currently have, I'd have to take 54 times 3, and then times that by 3, and then times that by 3, and another 3, and another 3, until I multiplied by 3 100 times to find this number. Now, I don't want to have to sit here and multiply by 3 100 times, so I want an equation that can help me find the number of boxes quicker. So one way to do this is to think about how we can use exponents to write our equation. So what I notice is in the first expression, in figure 1, I started with 2 boxes. In figure 0, I started with 2. In figure 1, I had 2 times 3 number of boxes, or 6 boxes. In figure 2, I took that 2 times 3, or 6 boxes, and I multiplied by an additional 3, which gave me 18. Well, I can rewrite 2 times 3 times 3 as 2 times 3 to the second. Well, then, to find the number of boxes in figure 3, I took this expression and I multiplied by another 3 to give me 54. Well, that's the same thing as taking 2 times 3 times 3 times 3, or 2 times 3 to the third. So if I wanted to find what the expression is going to be for 100 boxes, well, if I know taking it to the first figure gave me 3 to the first, and taking it to the second figure gave me 3 to the second, and figure 3 gave me 3 to the third, I can guess that figure 100 is going to be 3 to the 100 power times my original amount of 2. And likewise, if I wanted to know how many boxes were going to be in any figure, well, I just replace an x with where the hundred's at. So it'd be 2 times 3 to the x. If I want to know any figure, I can just plug that number in as my exponent on the 3, and it'll tell me how many boxes there are. Now, ultimately, this last one gives us a formula for finding any number of boxes in any given figure. We would write y equals 2 times 3 raised to the x. Okay, and in fact, all exponential functions will follow this same general pattern. Okay, in our current example, 2 represents our starting amount, how many boxes we originally started with. So that's like the start. Okay, how many things did you start with? We started with 2. The 3 represents what we were multiplying by every time we jumped 1 over. So this I call the multiplier. Okay, when we make one jump, that's what we're multiplying by. The x represented the figure we were currently on. Okay, so if I was in the first figure, my x was a 1, so I was taking 3 to the first. If it was figure 2, my x was a 2, and I was taking 3 times 3. If it was figure 3, my x was a 3, and I was taking 3 times 3 times 3, and so forth. Okay, so that represented what figure we were dealing with, and y dealt with the number of boxes we have in total. Okay, but like I said, it actually turns out that all exponential functions will follow this model. This number will always represent your start. The number with the exponent on it will always represent your multiplier. Now, one thing about the name exponential functions. We call these functions exponential functions because the variable, the x, is in the exponent, hence the name exponential function. Now, let's look at some examples of writing more exponential functions like this. Specifically, we're going to be looking at what happens when we're given a table. So in number 1, they give me a table and they want me to write an exponential function for this table. So I'm going to write y equals, and I want to know how many am I starting with? Well, when I look at this table, I want to know how many are in figure 0, or what amount do I have when x is 0? Well, in this case, it's 2. So I get a 2 as my starting value. Then I look down the table. As my x's increase, how is this pattern changing? What type of jumps am I making? Well, 2 to 6 to 18 to 54 is multiplying by 3. So my multiplier is a 3. And then it's an exponential function because every time I jump down the table, I'm multiplying by an additional 3. I put an x as my exponent. Notice that I get the same equation that I had from the pattern as I did this table. My starting was 2, just like the number of boxes was 2. My multiplier was 3, just like up there, my multiplier was 3. So my equation is the same. All right, let's look at a different example. Let's look at number 2. In number 2, my starting amount here is 40. So I'd write y equals 40. Then as I jump down the table, I notice it doesn't seem to be multiplying. It seems to be dividing by 2, right? 40 divided by 2 is 20. 20 divided by 2 is 10. 10 divided by 2 is 5. The thing to remember, though, is that anytime you divide by a number, that's the same thing as multiplying by the reciprocal. So 2 is the same thing as 2 over 1, and the reciprocal of 2 is 1/2. Notice each of these is getting cut in half. It's getting multiplied by a half. So I start with 40, I multiply by a half every time, so my equation would be y equals 40 times 1/2 to the x. Now, it's also important to note that not every equation is an exponential equation. Notice in number 3, I have a starting amount. I start with 7, so I have y equals 7. However, it's not multiplying or dividing when I move down the table. Instead, it's adding 2 each time. 5 plus 2 gives me 7, 7 plus 2 gives me 9, 9 plus 2 gives me 11. There is no multiplication going here. Well, exponents deal with multiplication, so this is not an exponential function. Okay, it is not. Instead, this is a linear function. What's really happening here is for every x, every time I make a jump, I'm adding an additional 2. So for example, when I had 0 x's, I just had 7. When I had 1 x, I added 2 and I got 9. When I had 2 x's, I was adding 4 and I got 11. This is a linear function. Okay, we looked at these first semester. What's different about our functions that we're talking about when we're talking about exponential is that we're having this multiplication happen. So our functions will be multiplying. Okay? So exponential functions always deal with multiplication. All right, let's just quickly recap what we've learned so far in this video. First, exponential functions are given their name because the variable is in the exponent. Second, exponential functions always deal with multiplication. And third, they always follow this general format. It's always going to be y equals whatever your starting amount is times whatever it's multiplying by for every x value that it moves. Okay?